Hello, everybody. Welcome back. We're going to wrap up boundary layers and external flows today. So let's see, what have we seen so far? Um, let's see. Uh, if let's see here, we saw that heat transfer by convection is in reality heat transfer by conduction through a boundary layer. And if the boundary layer acts as an insulation layer, such that thick boundary layers are more insulating and have lower heat transfer, and thin boundary layers have higher heat transfer. That we knew since very early on in our class. But then we did an analysis of one particular type of boundary layer, that is the one that would relate to molten metals, which are not so common, but they are easier to analyze. And we saw that there is an analogy with the heat transfer in a boundary layer, in this case, and the heat transfer in a semi-infinite solid. They don't look at all the same. They look very different, but the math is the same. So we could leverage in the math we knew from the semi-infinite solid, and we learned then that the boundary layer, we can predict the thickness without having solved any particular equation, just doing algebra using what we knew. And we learned that the boundary layer has like a parabolic profile, right? Like a square root, like we see in these two drawings. Okay, oops, let's see. In these two drawings. Okay. In these two drawings we have here. So the x is the direction, is the coordinate in the direction of downstream, the flow, downstream. X equals 0 corresponds to the leading edge of a flat plate, like we made a schematic here. The thickness we called YCT, that is kind of a funny name, right? That is the characteristic distance in the Y direction, right? And T because it's thermal. And we saw that there are two boundary layers. Now, this boundary layer that is that starts thin and gradually becomes thicker, right? Means that it's going to be more insulating downstream and pretty little insulating, highly conductive near the leading edge. And sure enough, using the expressions we know, we can estimate the heat transfer coefficient, H, the convection coefficient, and we would see that the convection coefficient decreases downstream and is very high at the leading edge. Right, and we also discussed that although math tells us that it goes to infinity, we know it doesn't go to infinity because the whole math we had done was based on 1D heat transfer in the Y direction, but when we are at the leading edge, the heat transfer goes in both directions. So that was okay. Then we said, okay, molten metals are cool, but we typically deal with gases or aqueous liquids or oil. So for that, we did need to pay attention to the viscous boundary layer. The viscous boundary layer that was developed by Prandtl and his student Blasius is something that was very painful to arrive to. I don't know if any of you read the bios I uploaded, but you can read that Blasius was not a happy student, was a talented student, but he said, this is not for me. But guess what? We're living on his work and we don't need to suffer what he suffered. And what from our point of view, all his suffering turns into one thing, that is this number 3 in this coefficient. That's all it is for us. And this is the thickness of the viscous boundary layer, right? No heat transfer, just the viscous part of the boundary layer. And what we saw on Monday was that then we can estimate a ratio between the two boundary layers, right? A thermal boundary layer and a viscous boundary layer. So now the viscous boundary layer is what it is. The thermal boundary layer is affected by the fluid flow. Heat does not really affect the fluid flow, but fluid flow affects very much the heat. So the calculation for the viscous boundary layer is the same for all cases. We're talking about the laminar case, right? But the thermal case, the thermal boundary layer, in the case of molten metals, in which the heat transfer, the heat had penetrated deep into the molten metal, and everything is moving with a uniform velocity because the viscous boundary layer is very, very thin. It's just like painted on the surface. So we could do that calculation easy. And when we compare Prandtl solution to the solution of the for fluid flow to the solution of the semi-infinite solid for heat transfer, we get that the ratio between the thermal boundary layer divided the thickness of the viscous boundary layer is this thing 0.6, which is, I'm going to call 1, is more or less 1, Prandtl to the -1/2. And here on Monday, I made a mental note saying, check out this -1/2 here, because it is going to tell us things. So when we see the -1/2, sometimes it's a 1/2, but what matters is it is a 1/2. These are problems for molten metals, not common, right? Unless you're designing nuclear reactors for submarines. But then we said, let's talk about air, water, and oil. And in that case, we could say things like air that has a Prandtl number of 0.7, let's call it 1. When the Prandtl number is 1, you can prove with math. And it's very easy, but I'm not going to be worrying about proofs. That if Prandtl number is 1, thermal diffusivity alpha and kinematic viscosity nu, which have the same units, and in Prandtl number 1 means they are the same, you plug the same number into the equations, and it tells you that the solution for the thermal boundary layer is exactly the same solution of the viscous boundary layer. Isn't this awesome? Because it took Prandtl a lifetime of pain to figure out the viscous boundary layer. And just for the case when alpha equals to equals to nu, right? When Prandtl equals 1, we say, you know what? Same thing. I don't even need to think about it, right? This is what is called the Reynolds analogy. Now, if the boundary layer, the thermal boundary layer, is much thinner than the viscous boundary layer, for example, the case of oils, then it's not exactly the same. But they share this thin boundary layer and the Reynolds analogy in which they are saying, they share something in common. And what they share is a gradient of velocities inside the thermal boundary layer. The reason we solved first the case for molten metals is not that everybody's working on molten metals. Nobody's working on molten metals. Well, I hope I didn't offend somebody in nuclear reactors for submarines, but the reason is that in that case, we did not need to worry about velocity gradients. But if you care about oil, like all of us do, now we need to worry about gradients. And gradients, the good thing was the headache of Blasius. So for the case of Reynolds analogy, I know it's exactly the same. But for the case of a viscous boundary layer, much thicker than the thermal boundary layer, so we still have, and in this schematic here, here in the right, we have a thin thermal boundary layer and a thick viscous boundary layer. So the velocity profile here is, and I think this velocity profile here tells us that the velocity at the edge of the thermal boundary layer is a small velocity. And within this thermal boundary layer, right, the thermal boundary layer that is thin here, we have a gradient of velocities between 0 and whatever small velocity we have. Because we have this gradient here, we're going to bank on Blasius solution. The gradient is not exactly the same because in Blasius solution, you have a little bit of curvature at the end. And in this case, you don't have this curvature, it's straight. But you know what? That's such a subtlety. I'm not gonna worry. I don't know anybody who worries. So we're gonna use the same thing. And when we do it, we would say that the thickness of the thermal boundary layer would be now a factor of 3, not the square root of pi or 1.77. Is this factor of 3 that accounts for the gradients. And instead of being u infinity, as the case of Blasius, right, is going to be a characteristic velocity that is this small velocity here, right? Because thermally, the heat transfer only sees small velocities because all the heat transfer is completed at low velocities, and velocities keep increasing and increasing because of the high viscosity of oils, for example. But for the heat transfer, it all happens narrowly. So if I say that thermal boundary layer is given by this, in which I'm banking on Blasius solution, then I could do these operations here that are very easy to follow, and we did it on Monday. And you come to the conclusion that the ratio between the thermal boundary layer and the viscous boundary layer now is not anymore Prandtl to the minus 1/2. It's Prandtl to the minus 1/3. Now, you know what? When Prandtl is 1, nobody cares because it's all the same. And even if it is not 1, it's not such a big deal. Other than that, this Prandtl to the 1/3 is a telltale that they are talking about air or gases, aqueous liquids, and oils, right? And things that have more from more or less 1 to much bigger than 1 Prandtl numbers, which most people use, right? So because we have this ratio, we can have expressions similar to the one we had before. We had talked how we tabulated the heat transfer coefficient, the convection coefficient. We didn't write H, we use Nusselt because it's a very general way of expressing it. So we have Nusselt and is 0.33, Reynolds to the 1/2, Prandtl to the 1/3. For the case of molten metals, if you remember, it was Reynolds to the 1/2 and Prandtl to the 1/2. So you already see this. This Prandtl to the 1/3 is going to keep appearing. And I went through all this pain of explaining these things and doing these triangles we did here, the similarity of triangles, to make sure that that you feel confident about what the hell we're talking about. Plugging and chugging, you don't need to take this class to do. You're proven that you can do that amazingly already. But if you understand, you can come up with your own things. Or when a colleague says, what should I apply? You would know which one. Or if a colleague says, I'm not too sure if this is right, you can take a look. If you see a Prandtl to the 1/2, and you're talking about liquids, about oils, maybe you should take a second look at this, right? And then we made it up to this point, and we said, so far, everything was about laminar boundary layers, right? Laminar boundary layers, the flow, the fluid is streamlined without oscillations, without perturbations. Now, very often, and some of my colleagues would say all the time, thank God in welding is not the case, but the flow is turbulent. So we need to know what to do with that. And what we discussed last time is that although turbulent, the transition from laminar to turbulent is gradual in a narrow range, but it's gradual, and we have a transition that I have indicated, I have a knowledge here. For the purpose of this class, we're gonna cheat a little bit and say the fluid can be either laminar or turbulent, right? Like overlooking the fact that in reality, there are some more details than those. And for the case, and the transition between laminar and turbulence will be determined using a critical Reynolds number. That critical Reynolds number that is in these notes, and by the way, I prepared the formula sheet. You don't have to use it, but many of you asked me if we had one. I prepared it. It's uploaded together with the biographies and together with the math refresher. And so these critical Reynolds numbers are all there. Everything in that formula sheet are things that are in the book, except the thickness of boundary layers that we do better than the book. But everything else, same as the book. You can use it, the formula sheet if you want or not, it's okay. The formula sheet is so big that there is possible that there is a typo. If there is a typo, you have to make sure that you do the right thing. And please tell me if you see a typo, and check with the book if you need to use any of those formulas, because we type them ourselves. Okay, so for the case of the flat plate, the critical Reynolds number is 5 times 10 to the 5. And because Reynolds number is velocity times distance downstream times kinematic viscosity, so this tells us what combination of velocities and length. For example, a very fast fluid might have a quick transition to turbulence. A slow fluid might have a slow transition to turbulence, but so you might need a very long plate to see turbulence. All these things you can say now. And this is amazing, because normal people don't know the difference between laminar and turbulence, much less are able to predict, okay, let me tell you when this is going to become turbulent. Normal people don't know that. But now you can say, I'll tell you here. You should not say exactly, because these things are starting to become somewhat empirical. And there are factors that affect it, like roughness of the surface, that are not accounted into these formulas. But although you cannot say exactly, you can say, this is a pretty good engineering guess, and that it is. So this is the last graph I showed, but I didn't discuss on Monday. And this graph is a graph that in the horizontal axis is not well marked, but this is the X coordinate. Leading edge here, and the downstream coordinate X is the horizontal axis. Vertical axis, I'm graphing two things. One is I'm graphing thickness of the boundary layer, in this one here, and in the other, I'm graphing Nusselt number. Let's start with the thickness of the boundary layer. Let's start with this. Because the Reynolds number depends on X, right? For small x, we have small Reynolds numbers, therefore we have laminar flow. So if this is the leading edge up to some point, which you get to see here because you see these transitions, we have laminar flow. Everything we have discussed so far, I already said everything I had to say about them. But when Reynolds reaches 5 times 10 to the 5, which is this point here, now the correlation, the formulas we had for laminar don't apply anymore. And we have new formulas. And now things start to get funny, because people can do PhDs on turbulence, and still turbulence is one of the big unsolved problems of engineering and physics and math, turbulence. So what we have is mostly empirical. Okay, the lines in the graph are too faint to see, but I can fix that, and I agree with that comment. Let's do. I'm trying to have a new page here. It's not letting me have a new page. Interesting. Okay, let's see. Insert. Okay. Okay, I got it. So I'm going to try to do these curves here. So horizontal axis is X. Vertical axis can be either of these two things. I'm going to start with the thickness of the boundary layer. So let's say we have a given U infinity, right? And we have a given kinematic viscosity. So at some point, we're going to have a Reynolds critical, right? That is 5 times 10 to the 5, right? And it's going to happen sometime downstream. So at the beginning, we would have a laminar boundary layer, right? And typically we used YCT, that it was 1.77 square root. But here, what I indicated is delta. That is what appears in the books on fluid mechanics. So, and this is a 99% boundary layer, considered at 99% of the final velocity, of the free stream velocity, 5x times Reynolds to minus 1/2. So far, we knew these things. We typically use YCT, but you'll see why I use delta here. And I'm going to do in blue here, the Nusselt number, which we already made a drawing, right? Something like that. And this is Nusselt 0.33 Reynolds to the 1/2 Prandtl. Damn. Okay, so that would be, okay. Oh, I think I know what's going on. Okay. Damn. Okay. So, all right. So somehow it is the thing refuses to cooperate, but I'm going to. This is Prandtl to the 1/3. Question to you: if I give you two choices, 1/3. If I give you two choices of fluid, I didn't say what fluid this is, but if I tell you this fluid is either molten sodium or water, what would you tell me the fluid is? All the information I'm giving you so far is this one you have on the screen. I like to see. I'm looking at the answers at the chat. Molten sodium or water? Yes, of course, it's water. Water has a Prandtl of 7, and therefore we should use the correlation for boundary layer, viscous boundary layer much thicker than the thermal boundary layer, right? And that is the one with 1/3. If this had been 1/2, then the answer would have been molten sodium, but we use that so seldom. Okay, so at the downstream, we reach the critical Reynolds number, and then what happens? The way we see things in this class is like magically we go from laminar to turbulent, acknowledging that that's not true. Really, we have a transition, but it's a relatively small transition. So now when we have turbulence, we have motion of the fluid that is chaotic and random. Motion of the fluid, what heat transfer mechanism is associated with motion of the fluid? Is advection. And if you remember, we can have advection and conduction at the same time, and we would have this Peclet number that would give us an idea of which dominates, if advection dominates or conduction dominates. And we know this, that if the velocity is high enough, eventually advection dominates. And this is what happens in turbulence. The more and more turbulent the fluid is, the more and more advection dominates. Now, if I tell you advection dominates, the next question is, and it's so bad we're not in person, but if I say advection dominates, the next question is, does then the kinematic viscosity matter, or does it thermal diffusivity matters? So I'm not going to make it too long, but the answer is no. It becomes secondary. They become secondary because the heat transport, the heat transport, that the momentum transport is dominated by the advection of the turbulence. So this is very interesting, because if advection dominates and advection is the same, because it's the turbulence is the same for heat transfer and fluid flow, you know what that means? That both boundary layers become the same. And so that's an interesting thing, because when we have turbulent flows, the thermal boundary layer and the viscous boundary layer become the same. Essentially, if we were to have like an effective Prandtl number, that Prandtl number would be 1, right? The Prandtl number that accounts for, that modifies, that accounts for the transport for advection. So, and in addition, not only they dominate and they become similar, but this transport is much bigger. This transport of heat and momentum is much bigger. So what do we see? We see that the boundary layer all of a sudden becomes a lot thicker, right? And the correlation for thickness of the boundary layer, right? And the book has delta. That's why I use delta for this part here. I don't like to use it, but I don't know what the YCT would be for turbulent flows. I would need to do some more research. That is hopefully going to happen someday. So that would be 0.37 x, and I follow down here. Reynolds x to the minus 1/5. Check out, minus 1/5. Why? And I don't know why, but it's a fact. And maybe nobody knows why. Some people try to do lots of computer simulations. Some people try to do deep math. I'm talking deep math, not the math I like. Deep. And some people do experiments and say this is what it is. I think this came from these experiments in which people say this is what it is. However, this factor of 1/5 is going to keep appearing. So put a note there, because you're going to see it. Now, from the point of view of the Nusselt number, something interesting happens. It's too bad we're not in person. The viscous boundary layer and the thermal boundary layer, all of a sudden they increase a lot, right? They are much thicker. So you might think, I have a thicker boundary layer, therefore I'm more insulated, therefore my Nusselt number would be lower. But that's not true, because although it's true that the boundary layer is thicker, the enhanced transport, because of this local advection of the turbulence, more than makes up for it. So what do we see? Yes, this boundary layer was thicker, but the Nusselt number still increases, and increases quite a bit. It increases so much that I would run into problem with my formula here. And then, of course, because the boundary layer keeps increasing, this decreases slowly. And this local Nusselt number, local, here is this formula. I'm going to put it down here where I have more room. Nusselt x equals 0.0296 Reynolds to 4/5 and Prandtl to the 1/3. this is no coincidence that here we have a 1/5 and here a 4/5. 4/5 is 0.8. Keep this 0.8 in mind, right? This 0.8 is going to appear again. So this is your local Nusselt number for turbulent flows. And this is semi-empirical. I don't know where the 4/5 come from, but I know it is 4/5, and you're going to see that appearing again. If instead of a local Nusselt number, you want to have an average number, which is more common, now you have to average over some part that is laminar and some part that is turbulent. And this is a formula in which you have these averages, right? Plug and chug. I'm not going to spend a lot of time here, other than you see this 4/5 here, which makes sense with this 4/5 for the local. And you see a Prandtl to the 1/3. This Prandtl to the 1/3 tells us they're talking about gases, aqueous liquids, and oils, right? I myself, I have a little bit of an objection to Prandtl being 1/3, but that's my own internal research. For now, we're going to take the Prandtl to the 1/3 like the book says. And that will be our official word. If you want to trace back these concepts to the book, here are the equations of the book. And that's why I asked you to get the 6th edition and not the newest 7th edition, because you can go and see where these formulas are and use them. All right. That was boundary layer for us. I want to take the last few minutes in getting into external flows, right? This was the conceptual part, but because we understand boundary layers, everything else now is going to come so much easier for us. So external flows, right? Let's start with a cylinder in cross flow. Guess what? Don't we use cylinders in chemistry or petroleum engineering and even in materials engineering, right? How do I calculate the heat loss of a cylinder that is in cross flow, right? So many things are cylinders in cross flow. So many, right? And I'll discuss briefly a little bit of the problem at a deeper level, so we enjoy it. So here we have our cylinder. The flow goes from left to right. We see that as the fluid hits the front, the leading edge of the cylinder, a boundary layer generates, and this boundary layer is going to get thicker and thicker, and this boundary layer eventually is going to detach into a wake, right? Because this is not like some sort of a Formula One car that is perfectly aerodynamic. Eventually you have this wake, and by the way, Formula One cars also have wakes, right? So you have this wake in which you have this like fluffy turbulence, right? And so before we talk about what everybody cares about, that is the average heat transfer coefficient, let's look at the heat transfer coefficient, the local heat transfer coefficient. And this is what we have. Heat transfer coefficients normalized in some way here in the vertical axis. And here's the angular coordinate. 0 is leading edge. This point here would be 90 on top. This point here would be 180. And what do we see? That if the Reynolds number is small, that means very slow flow, the heat transfer is high at the leading edge of the cylinder. And we know that because the boundary layer is thin. And the heat transfer gets lower and lower as the boundary layer is becoming thicker. And then when we have a wake, this fluff part here, the heat transfer coefficient is actually fairly low because this wake is not turbulent enough to enhance the heat transfer, right? And so this would make sense to us. If I increase my Reynolds number, I would still have like a leading edge that is fairly high heat transfer, like when we are facing the wind. And as the wind comes around, the cylinder would come around our face, the heat transfer is lower and lower, so we would feel less and less cold. But in the back, the heat transfer stays low. However, with higher Reynolds numbers, this wake starts to become more intensely turbulent, and it starts to have more heat transfer. Of course, because more turbulence means more local advection that it starts to dominate over the viscosity or the thermal diffusivity. It gets interesting when we have these little humps here. What happens, and those of you who play golf might know this already. So what happens is that if I have a high enough Reynolds number, my boundary layer might become turbulent before the wake. And there is something very interesting about turbulent boundary layers because they stick. So in a golf ball, you have the dimples to create, to trigger turbulence such that the boundary layer, the turbulent boundary layer sticks and doesn't have a wake. And for that reason, the drag, the aerodynamic drag is lower, and that's why the ball can go farther. If you have a golf ball that has no dimples, it's gonna go nowhere, right? That's why we have dimples in the golf balls. And that's what we see here. If you don't have dimples, it gets to a Reynolds number that is high enough in which you have a similar effect. You trigger the turbulence in the boundary layer sticks, and you have a much smaller wake. So you have this enhanced heat transfer, and then the heat transfer gets big. Why does it get big? Because we have a turbulent boundary layer. And then it gets low. Why? Because we have the wake. And then if we have like really high Reynolds number, same story. We start laminar, we trip into turbulence, and we have a very enhanced heat transfer because we have a turbulent boundary layer. And then as we transition into a wake, our heat transfer decreases. But the Reynolds number is so high that the wake is already quite conductive. Isn't this super awesome? I think this is amazing. You know, the type of things this says, that if we design a pipe, for example, in a burner, and we design a pipe carrying fluid in a burner, and then we do a calculation of average heat transfer, we might be happy with ourselves. However, the heat transfer in the direction of the flow of the combustion products, right, would be very, very fast, but on the wake the heat transfer might be very small. So for example, when in the front, in which the heat transfer is very fast, we might be burning our pipe. Those type of things happen, right? And they are due to local heat transfer, not to the average heat transfer. Okay, but let's talk about average heat transfer. That is the way we design most things. The concept of local is just to make sure we don't mess up. But overall, in general, we design for average. So these formulas are empirical. But I'll draw your attention to this. Here is Nusselt, with the bar meaning average Nusselt. And this is a formula, H bar. So in the end, we care about H, but they tabulated everything in form of nu. So it says, if you want a pipe, to calculate the heat transfer in a pipe, you have this formula. Look at this. C times Reynolds to the something times Prandtl to the 1/3. This is almost exactly, well, it is exactly what we have here. Let me find a formula. Look at this formula. For a flat plate, we have Nusselt is a coefficient, right? A coefficient times Reynolds to the something times Prandtl to the 1/3. What do you think this is? If you look, these formulas say this is for Prandtl bigger than 0.7. Of course, I didn't need people to tell me this because I know this 1/3. And you know why they picked 0.7? Because that's air. If they said, oh, for Prandtl equals 0.7, we should use a correlation for Prandtl less than 1, right? That would be a pain. We would have two formulas for everything. So you're going to see Prandtl 0.7 all the time, just because they say, oh, it's more or less 1, and it's air, and it's so convenient. So this coefficient, right? This coefficient is what it is, but you get to see that for a flat plate was 0.33, and for a square, guess what? These two flat sides, they give you 0.304. Isn't it kind of close? I think it is kind of close. And then you have this coefficient m, right? For a flat plate, this exponent m, for a flat plate, m was one half, right? And see, for the square, it's 0.59. It's not really 0.5, but kind of, right? So that's why I wanted to go through all these understanding of the boundary layers. Most people would say, oh, plug and chug, I'm done. When we have the quiz on Monday, that's what you're gonna do, plug and chug. But you know what? We would be missing all the beauty and all the understanding and all the ability to tell colleagues, hey, this is okay or not okay, because we understand what we're doing, not just because somebody told us. But things get better, because we said that if we have a high enough Reynolds number, we would trigger into turbulence, right? And if we are turbulent on the plate, we saw that it was Reynolds to the 4/5. I don't know why, but that's 4/5, right? 0.8. Look here. If we have a high enough Reynolds number, look at the exponent for Reynolds. So this is a cylinder. Doesn't look at all like a flat plate, because it's not. However, because we understand the concept of boundary layers, we understand immediately, aha, 1/3 air, water, and oil. M that is more or less 0.5, aha, laminar. Oh, M that is more or less 0.8, turbulent. I don't need people to tell me. And by the way, the book doesn't tell you, but we know, right? So now, once you did the square, you might as well put the square in different directions. You can put a hexagon in different directions. You can put a thin plate. The sky is the limit. This is what is in your book. But if you go to the literature of heat transfer, you're going to find people who put everything into this type of tests. And you know what? They always get a formula that is C times Reynolds to a something times Prandtl to a something. And Prandtl is 1/2 or 1/3, kind of, depends. And M is 1/2 to 0.5 to 0.8. And this is the way you design the heat exchangers, and this is the way you design the machines we have in this province. And this is the way you design the rockets for SpaceX. And this is the way you design Formula One cars. And this is the way you design nuclear reactors. This way. This is not Mickey Mouse. This class is for real. Okay, so you might say, hey, how about if I have a fluid that has strongly temperature-dependent properties, such as oil, right? So in that case, different correlations take different approaches, but this is the way you go about it. They say C times Reynolds to the something times Prandtl to the something. All these properties are evaluated at the free stream velocity, the temperature of the free stream, right? However, in the boundary layer, you have a range of properties between the temperature of the surface of your pipe and the temperature of the free stream. What they do, and this gets into really difficult math, difficult enough in which people say, you know what, screw it. Put a pipe in some sort of a wind tunnel or an oil tunnel and start measuring. And they came with this correction factor that says Prandtl, that you multiply this same formula that you had before, very similar, you multiply it by Prandtl at the free flow, right? Prandtl at T infinity, divided Prandtl at the surface temperature, which is not the same, right? Even if thermal diffusivity is more or less the same, viscosity changes very much in oils. And Prandtl is kinematic viscosity divided thermal diffusivity. And they found out is to the 1/4. This 1/4 is not the result of some fancy equation. This 1/4 is because they got 0.25 143 or something, and they say, okay, I'll cut it off at 2.5, at 0.25, because actually the scatter is bigger than the next digits. So cylindrical cross flow, 3 minutes I have. This is the way you're gonna solve problems for the rest of eternity in the plug and chug way when we do convection. So number one, you have to know that the ultimate goal is to get H. Everything we have done so far was, if I give you H, you calculate lump capacitance, or you calculate a bunch of other things. What we are seeing this week and next week and the week after next is, how do I calculate H? And how do we do it? So we do it standing on the shoulder of giants. So we select the right formula for a geometry. So you say, oh, flat plate. Okay, somebody ruined his or her life in generating all these correlations. You might say, no, I don't care about flat plates. I want, what do we have? A cylinder. Okay, here you have a cylinder. Oh, no. I want to do a sphere. I'm talking about a falling drop, like in welding. So you find the formula for the geometry. Sometimes you have crazy geometries that don't have formulas. In that case, you either go to the literature and maybe somebody did it, or you start like saying, this looks like this or looks like that. The amazing thing of convection is that in the end, you're going to end up more or less being factors of 10, 100, or 1,000, as we have discussed. Second step, you calculate Reynolds and Prandtl, and sometimes you need other factors. And you do it at the reference temperature they tell you, right? For example, this formula says the reference temperature is T infinity. That is the temperature of free flow. This formula is based on the film temperature. The film temperature is in the notes, is you take surface temperature, you take free flow temperature, and you do the average. That's what they call the film temperature. So you calculate Reynolds and Prandtl, and please, I taught so much theory now over the last 2 weeks. This might be sickening by now. We have so many problems that you can use from previous years that are all worked out and had the solutions done in my own handwriting. Please take a look. So once you calculated the Reynolds, for example, in this case, and the Prandtl, you calculate nu. And once you calculated nu, you unpack nu. Nu is HL over K. So you flip that formula and you calculate H. And after that, then you can start doing everything we have been doing so far, like lump capacitance and whatnot. Plug and chug. Many of my colleagues don't like teaching this class because they think this is all there is to heat transfer. No, heat transfer is beautiful and awesome. These formulas are just like the pinnacle of the accomplishments of many people over hundreds of years. Okay, so I have an example to discuss, but we're going to do this example quickly on Friday, and we'll start with internal flows. And we can stop here, and I'll see you all on Friday. Thank you very much.